Hey everyone, welcome to another episode in Physics is Fun. Today is going to be an introduction to force problems, starting without friction. Let's jump into reading the question. Two objects are connected by a massless string that is over a frictionless pulley. One object hangs and the other is on a frictionless incline. The masses are m sub 1 equals 2.0 kilograms, m sub 2 equals 6.0 kilograms, and the angle theta is 55 degrees. A. Draw free body diagrams of both objects. B. Find the magnitude of the acceleration of the objects. C. Find the tension in the string. And D. Find the velocity of each object 2 seconds after being released from rest. Let's draw the picture now for the problem. There is a triangle with a frictionless pulley on the top vertex. A mass m sub 1 hangs from a massless string under the pulley, and over the pulley a mass m sub 2 is hanging on the incline. The angle theta goes here to complete the picture for the problem. Let's now draw the free body diagrams for part A. For the free body diagram, for mass sub 1, start with a base dot, and the mass has a force downward of m sub 1 times g, or gravity, as we are on Earth. In the opposite direction, the mass is hanging by the string, so there is a tension force holding the mass up in the air in the string. With this start, mark a coordinate system to define our directions and to help with the future body diagrams. M sub 1 is touching the y-axis and moves in the y direction with no forces in the x direction. M sub 1 was simple, but looking at M sub 2, it is an angle on the incline. Since for M sub 1 we marked for its movement direction, the other mass will move down the incline. For the coordinate system, let's make the x direction point directly at the angle the mass will move at, tilting the axis clockwise, and starting with a base for m sub 2, and let's dash out the positive axis. Looking at m sub 2, it has weight down as well, of m sub 2 times g, as it is also affected by Earth's gravity. Let's dash out more of the axes, and from the picture we can write out the angle theta here. With the angle here, trig does not seem to help, so we need to manipulate the angle closer to the origin to be able to split the force vector into x and y components. Currently there is a right triangle we made, so looking at the angles, we have the 90 degrees from the right triangle and theta. And the angle that must be left, touching the origin, should be 90 minus theta. If this angle is 90 minus theta and is on the right angle of the axes, then the other side should give the other angle of just theta, like so. With this theta, we can use trig now to find the x and y components. Moving on, the tension is in the opposite direction of movement, so the negative x direction. And finally, this mass is sitting on an incline, and since it's not breaking through, a force is exerted back onto the mass in the positive y direction, which is our normal force, n sub 2. With the free body diagram drawn, let's write out the sum of all the forces in each direction. For m sub 1, there are no forces in the x direction, so moving to the m sub 2, we have our tilted axis, so the x-axis starts with the weight. So for the x component from the diagram, m sub 2 times g times the sine of theta minus the tension in the opposite direction will equal a moving resulting force of mass times acceleration, so m sub 2 times a. Now in the y direction, m sub 1 has the tension minus the weight, m sub 1 times g, which will also have some moving resulting force of m sub 1 times a. Because both masses are on the same single string, our acceleration will be the same for both attached masses. The tension throughout any string in a system should be the same. When more strings are introduced, it will potentially have different accelerations and different tensions. Moving on to m sub 2, There is the y component now. M sub 1 times g times cosine theta minus normal force n sub 2 equals a moving resultant force of m sub 2 times a. With all our sum forces written and free body diagrams drawn, let's move on from part A. Part B asks to find the acceleration of the system. Since we found the acceleration to be the same, we can just add all of the sum forces to be able to solve for acceleration. To add the forces, add the left sides together and the right sides together. So now it's time to calculate. Let's write the left side of the m sub 1 equation to get t minus m sub 1 times g, adding to the left side of m sub 2 to get plus m sub 2 times g times sine of theta. This all equals the right sides m sub 1 times a plus m sub 2 times a. We should notice we have a t and a negative t, so those can cancel out. And to rearrange and leave m sub 2 times g times sine theta minus m sub 1 times g equals the right side, and we can actually factor the a out of both terms to equal a times m sub 1 plus m sub 2. With the a by itself, we can divide the rest on the right to completely isolate and solve for it. Divide both sides by m sub 1 plus m sub 2 and cancel on the right side to get a final acceleration of a equals m sub 2 times g times sine theta minus m sub 1 times g, all divided by m sub 1 plus m sub 2. Plugging in values now, we can solve for a equals 6 kilograms times 9.8 meters per second squared times sine of 55 minus 2 kilograms times 9.8 meters per second squared, all divided by 2 kilograms plus 6 kilograms. Each term has a kilogram, so all of the kilograms can just cancel out from all four terms. Multiplying out, a equals 48.166 meters per second squared minus 19.6 meters per second squared, all divided by 8. Giving a final answer of a equals 3.57 meters per second squared. Part B is solved for acceleration equals 3.57 meters per second squared. Moving on to part C, we need to find the tension in the string. Our tension is in two equations, t minus m sub 1 times g equals m sub 1 times a, or m sub 2 times g times sine theta minus t equals m sub 2 times a. The first one looks much easier, so with that, it's time to calculate. Rewrite t minus m sub 1 times g equals m sub 1 times a. And now add m sub 1 times g to both sides and cancel on the left side. This gives t equals m sub 1 times a plus m sub 1 times g. Plug in numbers now to get 2 kilograms times 3.57 meters per second squared plus 2 kilograms times 9.8 meters per second squared. And now get a final tension, T equals 26.74 newtons in the string. With part C solved, let's move on to the last part D. This is a small review to link back to kinematics, and so we can have a relationship with velocity and force that might have to be used in the future. Remembering kinematics, there are three main equations, and we are given time, and we are not given any distance. Let's write out the variables we do have with acceleration equals 3.57 meters per second squared, time initial equals 0, time final equals 2 seconds, velocity initial equals 0, and velocity final is unknown. With these variables, we can easily plug into the equation velocity final equals velocity initial plus acceleration times time final minus time initial. With the equation, it's time to calculate. Rewriting velocity final equals velocity initial plus acceleration times time final minus time initial, and we are solving for velocity final, so let's now plug numbers in. Velocity final equals 0 plus 3.57 meters per second squared times 2 seconds minus 0 seconds. Crossing out the 1 second, this gives the answer velocity final to be 7.14 meters per second. With part A all drawn out, we were able to use the force equation and solve part B for the acceleration of the system at 3.57 meters per second squared, and solved part C with the tension being 26.74 newtons, and finally solved part D to review and connect kinematics to get a final velocity of 7.14 meters per second after 2 seconds. I hope these intro problems are as helpful for you as they are for me. Thanks so much for watching, hope you come back to learn more exciting material, and I'll see you next time.